Hello, everyone. My name is John Coker, and my talk today will be on dual deployment for rocketry, particularly high-power rocketry, but can also be used for model rocketry and mid-power rocketry. I'm happy to answer questions as we go, so please feel free to use the Q&A tab on the right, and I'll try to pause after each slide and answer questions. Okay, so here's what we're going to go over. I'm going to review the standard motor ejection that you're familiar with because some of these components will be useful later. We'll talk about different ways of doing deployment, getting into electronic deployment, which is a prerequisite for dual deployment, obviously. Talk about electronics phase, wiring and testing, other ways than the standard dual deployment mechanism. We'll use up whatever time is left at the end for Q&A, but again, feel free to ask questions by typing it into the Q&A tab on the right, and I'll pause after each slide and answer any questions that come up. So let's talk a little bit about how events happen. Let's start with motor ejection because that's something that everybody's familiar with. So here is your standard Estes motor. The propellant burns, sending gases out of the back during the powered flight phase. The delay phase burns when the propellant burns out. The delay charge starts burning, and that's what creates the time delay. And then when the delay charge is done, the ejection charge fires, and that's the event. So this is kind of the prototype of how these were done because model rockets, and particularly Estes rockets, were the genesis of the hobby. So this is kind of the reference that we'll use even when we get into different kinds of motors and electronic ejection. We'll still tend to use these phases, these ways of thinking about things, and in particular, this will be important reference for timing. Again, the propellant burns entirely, then the delay burns for its length entirely, and then the ejection fires. So that's kind of the model for ejection. Now, if we look at a composite motor, it's very different in construction. So instead of burning from the end, they generally use base grains, which means that it burns from the middle out. Sometimes there's a moon burner, so it'll burn up one side and out. There are, of course, end burning high power motors as well, but most commonly we see base grains. And because of that, now the function of this motor is different in the sense that because it's not an end burner, the delay doesn't start after the propellant grains are done. It, in fact, has to start at the same time as the motor ignites. So really the delay charge is longer. However, for consistency, we're going to talk about it as though the length of the delay starts after the motor burns. If you buy a motor from Aerotech that has a 4-second delay and the burn time is 2 seconds, that delay really has to delay for 6 seconds. So, but for consistency and simplicity, let's consider that the delay length starts after burnout. So after the motor burns, the ejection charge burns, and then fires. So that's pretty standard. The only real complexity is the grain geometry means that the delay charge may be burning at the same time as the motor. Okay, so let's talk a little bit about this. I know that there's been some confusion about things, and some manufacturers have tried to introduce FUD about ejection. So let's talk about this. The ejection is always black powder. And in black powder motors, it's just part of the motor. And in composite motors, you just add it into the forward well if it doesn't already come in. So really we're not, composite motors and black powder motors are basically using the same mechanism for ejection, which is fine black powder. So again, just to be consistent, we always count the delay length from motor burnout, even if they're burning concurrently. So one of the issues with motor ejection is you have to know how long of a delay you should have, because you ideally want the rocket to open very close to apogee. And the bigger the rocket, the more important this is, because if the airframe is moving with significant speed, the parachute will snap when it opens, and that force of it snapping open could cause too much stress on the recovery system. So for model rockets, not critical. The bigger the rockets get, the more critical it is to have good timing. Now, the other problem with delays is, in many cases, they're fixed length, and even when they're adjustable, the mechanisms for adjustable are pretty wonky. I mean, if you've played with the delay drilling tools or different calibrated length drill bits, you know this is a pretty imprecise thing. So it is possible to adjust delay lengths, but not super confidence inspiring. So let's talk about, when we move beyond motor ejection, what different arrangements look like. So for motor ejection, we basically have our motor, the recovery system in the same tube but forward of the motor, and a nose cone. So this is sort of your simple thing. Motor ejection fires, nose is pushed out, laundry escapes. So the other arrangement, once we start using electronics, now we're not limited to initiating the ejection charge from the motor. We can initiate it from any part of the rocket. So the sort of another arrangement here is to put electronics in the nose cone. Again, there's a single chamber for the recovery system. So the nose cone separates it, the laundry escapes. Now, another common arrangement is a separate electronics bay. Here we have a section of the rocket that is dedicated just to the electronics, and it may or may not be part of the nose cone area. So again, opens up the rocket, there's a single bay. So all these are sort of variations of the same way to open the rocket. The second two are different ways to place electronics. The first one is the well-known motor ejection. Now let's get to dual deployment. Now this gets a little more complicated, because in dual deployment, by definition, you have two phases of recovery. You have a phase at apogee, which emits a drogue, and then a phase at a low altitude that emits the main. So this means you need two different sized parachutes or streamers, and usually two different bays to contain them. Now, we'll talk at the end about other arrangements, but this is kind of the canonical way to do it. So here is the rocket prepped. At apogee, it separates. The drogue parachute comes out, and then it descends quickly. And at the low altitude set point, the second charge fires, the main parachute comes out and brings the rocket down gently, but not drifting too far, because it's only coming down a large parachute for the last little bit. So this is how it should look. Basically, sorry, this is a very old photo. This was actually taken with a film camera, if you can believe it. So there's the big parachute at the top. That's the main parachute. Then you see a Nomex blanket, nose cone, the main airframe, another the drogue parachute and Nomex blanket, and then a long bridle, and then the booster section. So this is kind of how it should look. So what are we doing here with dual deployment? So the real goal is we want the rocket to come down fast. Now, why do we want that? Well, if you're flying high, you want that because if there's any winds aloft, they'll carry the rocket far away and you may lose it. Even if you're not flying particularly high, if you're flying in a space where you have a limited area or there are trees or other things you don't want to get involved with, you may want to keep the rocket close to where it launched. Now, the other thing is you can But with dual deployment, you can avoid the trade-off between a large parachute for a soft landing and a small parachute for quick descent, because you can have both. So why would you want a large parachute? Well, if you're flying on hard surfaces, like the desert in particular, these are very hard on rockets. The other thing is if you have a heavy rocket, you probably want to overshoot it, just because the harder, heavier rockets, more mass, harder hit even at a certain speed. So it's just nicer to have a larger parachute for the very last bit. So again, this really came about because of high altitude flights, so the rocket didn't drift away forever, because often the winds at high altitudes are very different from the winds on the ground. And again, for hard surfaces, it's important. Now, obviously, it's a lot more work to build and prep the rocket, so that's the downside. That's a downside. And again, you have to get into electronics, and there's more expense in airframe components, and you need an extra parachute generally. Okay. So let's talk now about electronic deployment, because this is probably the biggest barrier to people getting into the higher end of the hobby, is because electronics feel daunting until you've done them. The good thing I can say for those of you who haven't tried electronics is it seems daunting before you start, but once you get used to them, you won't go back. You can just avoid so many problems and inaccuracies. It'll just be part of every rocket you build. So electronic deployment. Basically, you fly a little computer, and that computer has one or more sensors. They generally always have a barometric sensor, and they may have other sensors to collect other data. So the flight computer basically tracks your rocket, figures out when it's near apogee, and it can do many other things too. It can do staging, they can do backups, they can even do other effects like outboards, etc. So basically now you have the ability to add custom events to your rocket other than just recovery. Another nice thing about electronics is you get information about your flight. They all give you altitude, and some of them also give you other information. They may continuously record altitude and acceleration. They may have GPS on board, many different things. So there's other benefits you get as well. So again, almost all the units are barometric sensors. I don't believe there's anything on the market with only accelerometer anymore, but they're generally a barometric sensor, which is the best way to measure altitude for rockets that don't fly very high. And the accelerometer can be useful for staging and detecting liftoff, detecting motor burnout, and also for other staging things. GPS is very nice also, in particular if you're flying high enough where the atmosphere gets thin, like these 100K shots, GPS is kind of necessary. But even with not flying so high, if your rocket's going tens of thousands of feet, it's nice because most of the GPS units have a way, or some of the GPS units have a way to telemeter their position back. And so you can go find the rocket based on its location. And some of the units also have telemetry where they'll actually report state like battery state, charge, continuity, everything to you continuously before flight, which is kind of very nice to look on your laptop and see that your rocket is still ready to go after you've gotten back to the pad and you're waiting for your turn. So electronics have a lot of nice additional benefits other than just recovery, but we're going to focus on the rest of this talk just on recovery. So here's a nice simple unit that's a good one to start with, okay? So it has a barometric sensor only. It supports apogee and main, so it supports dual deployment. It reports the peak altitude. It doesn't have any other data functions, but it gives you the most important single piece of information. It fits in relatively small tubes, so it'll fit in a model rocket tube, and it's relatively inexpensive. Another unit that is nice to use is the bigger brother to that one. So their RRC3 has the same dual outputs, but it also has records flight data. And so if you want to be able to see graphs of your rocket's performance in flight, that's kind of nice. It's also modestly sized. It fits a BT-60 29 millimeter tube, and it's not terribly expensive. Another unit that I've used a lot is the Altimeter set of products, so particularly the telemetrum, because now here you start to get some of the real nice benefits. It has a barometric sensor, of course. It also has an accelerometer, and it can use sensor fusion to detect more things about the flight. So you get a little bit more accurate staging and things like that. It has dual outputs only, so they have bigger versions of this that have 4 outputs, but this one has 2 outputs. It has a GPS sensor. Now, one really nice thing here is telemetry. So this will report the state of the charges. It'll report the state of the battery. It'll report its GPS location continuously. So both in flight and while you're on the ground. So you can know when your rocket, when they push the launch button, your rocket is still good to go. This is a really nice feature. And then, of course, because it's constantly transmitting the GPS location, it's easier to recover it because you can just drive over to where the last location you got was, and the rocket should be close. Now, of course, with all these capabilities, it's more expensive. I think right now about $300. There are many manufacturers. I haven't used all these, but these are the ones that appear to be currently available. They come and go all the time. So some of the ones that I'm most familiar with are no longer in business, and there's some new ones that I've never used. But I'm sure if you ask people at your section, there'll be somebody who's used each of these units who can give you more information about them. Okay, so let's talk about electronics bays. You have to protect your electronics and keep them secure. And so typically you use a separate section. Now, some units can be put into the recovery area itself, but the black powder ejection charge is pretty nasty, so you generally isolate them. So the altimeters need to be secured, particularly if they have an accelerometer. If they're barometric only, that's less important, but generally you want to protect them physically as well as in terms of the exhaust gases. Protecting from the ejection charges is a key part of the electronics bay. And one of the other things, though, is the electronics bay needs to be able to equalize its pressure inside with the pressure outside. This is important so the barometric sensor is measuring the air pressure and therefore the altitude of the environment of the rocket, not just the bay. The battery is one of the more difficult components to deal with because it's heavy. So you have to have solid support for that. Generally, you want power switches so you can arm the unit when it's on the pad and not before. And you need to arrange the ejection charges. So first of all, to secure the altimeter, generally they come with holes. And the most common way is to mount them on a rigid board with standoffs. So here is a piece of 1/8 inch plywood, but G10 or phenolic sheets or various things are all reasonable materials. Plywood is nice because it's easy to work with and easy to buy and not too expensive. I strongly prefer zip ties for mounting the batteries. I know some people like to use battery holders, but I think it's just another source of failure. So I use zip ties for them. And I generally put the switch right on the plate itself with an arrangement so that you can see the switch mechanism through a hole. And nowadays, though, you'll see a lot of really slick bays made custom for rockets and the electronics and 3D printed. So that's probably will be more common in the future. So here you can kind of see how everything's sealed up. You can see the little switch here. This is actually a slide switch that I've painted white so that it's easier to see when you're out in the bright sun in the field. You can see the charge coming out on the left, and obviously you need to be able to open it up, prep everything, and then close it. And you need to be able to arm it after everything's closed, just for convenience out at the pad. So you need to, again, as I said, vent to the outside. So I don't know exactly where this started, but Tommy Billings always made a big point that you should have 1 or 3 vent holes, not 2. So I've always done that, 3 or 1, but not 2. The vent holes sizing isn't critical. I mean, generally you can go oversize. I usually use somewhere around 1/4 inch holes, just to make sure that there's unimpeded airflow. And I generally take advantage of these vent holes and access the switch through them. So again, batteries are some work to manage because the batteries are heavy. And so they're generally the heaviest thing inside your bay. So you need to have them secure. Again, I like zip ties. Some people use battery holders, but even if you use a battery holder, make sure you use a zip tie to keep it in the holder so it can't slide around or pop out. Power switches. Okay, so the tricky thing with power switches is they need to be securely mounted, but also they need to be accessible from outside. Again, when you walk out to the pad with your rocket, all the power has to be off. And then you put it on the pad, raise the pad to vertical, and then you arm everything. So just keep that in mind when you're thinking about how to arrange things. You don't want to have to take the rocket apart at all. You want to just be able to arm the electronics at that point with the rocket on the pad vertical, ready to go. So everything has to be accessible from outside. As far we could have a whole talk on switches. The one thing I will say is make sure it's a switch that feels solid in its on and off position, and there are no extra positions. You don't want to have anything where you're guessing when you're out on the field. So make sure that it's very clear when the switch is on and when it's off. No middle position, no sort of, I think it's far enough kind of guessing. Okay, so electronic matches. So basically the altimeter is going to apply a current across 2 of its terminals, and then that's going to fire an E-match. So you need to wire the E-match to the altimeter, and then you need to get it out of the bay and into the recovery section of the rocket. Again, I find that it's everything I do out on the field is twice as hard. So I try to prep as much as possible in the shop, and I try to make sure that whatever I do in the field is easy. You know, the fewest number of loose screws, the least amount of work that I have to do in the field. So just keep in mind that ease on the field is much, much more important than ease of building. And the other thing, remember, the black powder charge is going to go off in the recovery section, so we want to protect the electronics bay internals from that. So what I generally do is I run the electronics, the E-match out through a small hole, and then I cover the hole with poster tack, and then I'll tape over it. So here you can see this is all wired and ready to go. The electronics, the E-match is coming out of a 1/8 inch hole, and that's sealed with poster tack and held down by tape. Okay, now obviously using electronics, there's more complexity. You have to wire them, and you're going to have to choose the size of your charge, which means you'll need to test that things work. So there's two main ways of wiring. So what I call style 1 is the electronics just have an output and a battery input. And in that case, you generally put the switch in line between the battery and the electronics. So when you turn the switch on, power goes to the electronics. There's also style 2 where the unit has kind of a switch arrangement built in. So you wire the switch to the electronics and the battery is permanently wired to the electronics as well. So that is essentially the switch is integrated into the electronics. You'll need to know which kind of arrangement your electronics have before you do the wiring. Electric match wiring, generally fore and aft for the main and the drogue. You'll need to figure out how much black powder to use for your ejection charge, and then you'll need to make the ejection charges. So let's start going through those. So here is a typical arrangement for what I call the style 1. So this simple altimeter does not have a switch built in. So I need to interrupt the circuit between the battery and the altimeter with the switch. I don't think it really matters whether you're on the plus or the minus side. I generally put the switch on the plus side, but I don't think it really makes any difference. And, you know, this 18 gauge is probably overkill for the wire, but it's easy enough to use. So whatever you feel comfortable with. Okay, so here's what I call style 2. This is an Altus Metrum Easy Mini. This has a switch wired separately. So you can see the two yellow wires running leftwards from the unit go to the switch, and then the battery is permanently mounted. So in this arrangement, the switch is part of the unit rather than having the user install it between the battery and the altimeter. So this, because the switch connects to dedicated terminals, then you're just taking advantage of the electronics to do the switch handling, but you still basically have the same amount of wiring. Again, I prefer stranded wire and 18 to 20 gauge. So now the electric match wires here, hopefully in this picture you can see a few different things. Generally, the electronics have a terminal strip, and the battery and possibly the switch and the outputs are all wired to that terminal block. So here you can see that wiring. The other thing that's I like to do is if you notice there's a small zip tie against the back of the plate, this is just to provide a strain relief so that while I'm prepping the rocket, I can't pull the E-match out. And the other thing you'll notice, see how on the plate it's stepped? This actually creates a little bit more tortuous passage for gases to get through. They have to get around the outside of the disc, you know, through the flat part of the step, through the lip. It's never going to be perfect, but the more you can protect the electronics, the longer they'll last. You'll see there's two E-matches here, one running aft for the drogue, and the other one running forward for the main. And anything else here? I don't think there's anything else that's that much. Oh, there's one other important thing. I have a good video that I'll refer to at the end, but be careful with electronic match wires because they're generally solid core, which means they're very easy to damage. With stranded wires, you can pretty much use anything you want, including diagonal cutters to strip. But when you're dealing with solid core wires, it's really important to strip them with proper wire strippers because otherwise you can nick the single core, the single copper wire, And then when you bend it, it becomes very fragile and it could break. And sometimes, if you're unlucky, you won't even notice because one will be broken and one will be connected. So it'll look like they're good, but you don't have continuity. So again, I strongly recommend using proper wire strippers when you're dealing with solid core wires. So the way to figure out how much black powder you need in your ejection charge, there's these ejection charge calculators that essentially take a volume and a pressure and tell you how much powder you need. So then you'll measure out that much powder and put it into the ejection charge. I recommend that you back off a bit and test up, because I find that usually those calculators are estimating high. So I usually back off 10 or 15% and try that first, and that's usually good enough. Of course, you can overdo it, but then it just puts more stress on the components of the rockets. It's not necessary. So to test, you don't need to prep the whole thing. All you really need to do is run the eMatch out and just touch its ends with a 9-volt battery. So testing shouldn't be that hard. Again, some of the videos that are linked on the end show this in progress. So it's probably easier than a slideshow. And another thing I've noticed, usually you're doing this after your parts are freshly painted. So just keep in mind that the nose cone and the airframe are probably going to fly apart. So maybe put them in a sleeping bag or something to protect the finish, since you probably just got done painting them. And so now we need to make the ejection charges. So here at the top is a electric match. This is kind of how they come. So the red cap is protecting the match head, and different people have different techniques. I prefer to use little separate charges, and I generally use centrifuge vials or other small plastic containers. Some people like to use aluminum electric match charge wells that are mounted to the ends. I don't think it really matters either way. I tend to do it this way because I can prepare the charges easily in the workshop and then bring them out and use them on the field without having to do too much work out in the field. So I prefer centrifuge vials. What I do is I drill a small hole, like maybe 3/32 in diameter in the bottom, and then I'll strip off the red cap, or white in the case of debut fires, off the end of the electric match and slide the wire in. And then I'll put a little bit of either silicone or epoxy around the wire and pull it all the way in. This just seals the bottom. Then once that is in place, you can pour in the black powder and pack it tight. It's generally this, by the way, what I'm showing you here is the normal process for rockets that are flying, say, under about 30,000 feet. There are other techniques that you'll want to use if you're going to fly higher. I'm not going to go into that in detail here, but it's easy to Google that. At that point, you either probably want to use surgical tubing charges or CO2 systems. But anyway, for normal sport rocket flying, it's fun. This is quick and easy. I also like to make sure that the black powder can't move around. You want it to be solidly packed against the charge. So I'll fill up whatever extra space there is in the vial with just Estes recovery wadding, so that then the cap closes tightly and snaps down and everything's locked together. So let's talk about where you go from here. So here's some other things you might look into. So there's other ways to do dual deployment. One of the first things that came up in the early days was, oh, I have this rocket that's set up for motor ejection. I want to do dual deployment. So then the first sort of impetus people had is, how do you do dual deployment with a single recovery bay? So this, you'll obviously still need electronics for dual deployment, but you may not need two separate recovery bays. So people have used things like cable cutters. There's several different ones out there on the market. There's also parachute reefing. So there are, there were a couple in the past. I think right now Jolly Logic is the only one that has a unit like this. They have a little unit that holds on to the parachute with a rubber band, so it kind of keeps it more or less ineffective until a low altitude set point. So parachute reefing is another way. Cable cutters are an interesting thing where you actually have two parachutes in the same bay, and when the bay opens, one of the parachutes comes out, but the other one is retained. And when the low altitude event fires, it actually cuts the cable that's retaining the parachute, and it can open up. So that's another technique for dual deployment when you only have one bay. Other people have played with solenoid latches, so actually running electric current to open a piece. I know Black Sky used to sell a unit like this. I don't know if any of them are still around, but that was one that was around in the past. And unfortunately, I think the cable cutter is still, these cable cutters are still available. The solenoid latches, I think, are no longer. I'm going to switch over to Q&A because I see it flashing. Sean's question is what pressure rule of thumb? I generally go to 12. You'll develop your own. Some people would say 15. I generally start with 12 and then just back it off by feel, but you'll get a feel for it fairly quick. And as far as the Jolly Logic, yes, I consider it to be dual deployment. So the reason I say it's dual deployment is because there's two events and the rocket descends at different speeds. So at the apogee, you open up the rocket and it starts descending quickly. By the way, you don't necessarily need to kick out a parachute at apogee. Just the fact that the rocket is no longer as aerodynamically efficient will make it fall more slowly. Generally, for larger rockets, you will actually have a small parachute, but sometimes you don't need one. You can have a streamer or even nothing. What usually happens if the rocket breaks into two roughly equal sized sections, it will sort of flat spin on the way down. And even though it'll come down quickly, it won't be too fast for the main. People have used smokeless powder. I've never tried it. Sort of as long as black powder remains available, I think it'll still be preferred. So check with your section. Usually somebody who's your motor dealer will be able to sell 4F black powder on site. If you live in an area that's less overrun with progressiveness as the one I do, then you may even still have gun stores where you can buy it. So, but 4F black powder is still available even in California, so it hasn't been a problem yet. Smokeless powders have different burning characteristics. I know that smokeless powders are supposed to match. Smokeless powders are very different from black powder. Now, there are black powder substitutes, blanking on the name, and those should work. But true smokeless powders, no, I don't. They're too explosive and they don't generate enough. But I think they operate too quickly. So I wouldn't recommend that. I have never needed to use Pyrodex, but it should replace black powder in exactly the same mechanism. As my understanding is, it's supposed to be a replacement for black powder firearms, so it should work exactly the same as black powder. I've just not had any experience with it. Another question is, how do you place the prepared ejection charges? I actually tend to tape them to the end cap of the electronics bay because I want them to be secure and not moving around. I try to make everything as locked down as possible, just so I don't have to worry about wires getting pulled. So I'll generally tape the charges right to the end of the bay. For people who are using charge wells that are mounted to the bay, obviously that's how it's going to be. But if the charge is loose, I'll still tape it to the bay. I don't think it matters if the charge is in front of or behind the parachute, because what you're really doing is just releasing gases to open up and separate the two sections. And the shock cord is going to pull the parachute out of the airframe as the pieces move apart through the ejection charge action and through the air. So it's really just a matter of opening the rocket. It's not really pushing the parachute out. I don't generally put the charge in a well. I usually just tape it to the end cap, and that seems secure enough. Generally, once everything's prepped, it's pretty tight in there, so things aren't moving around too much. But I just mostly prefer to tape everything down, just so it doesn't move around, I don't snag anything, or I don't pull any wires while I'm putting the rocket together. Yes, so the question about a drogue charge at apogee and then pulls the main at lower altitude. Yeah, that was what I was trying to explain with the cable cutters. So essentially, you can imagine, I should have made a diagram of this, but essentially you can imagine the shock cord is attached to the main, and then a shock cord is attached from the main to the drogue, and also the main is retained by a separate cable to the rocket, so it can't escape. So when the airframe opens, the drogue comes out, and it's pulling against the main bridle, but it's also pulling against the shorter tether. So the main is stuck inside. And then at low altitude, the cable cutter cuts that secondary cable, and then the drogue parachute can pull the main out. And this is kind of what drogues were really supposed to be for. They're a way to make sure that the main comes out neatly, but we generally refer to drogues we use it as the only parachute at the high altitude. David asks about all thread. I use all thread. In fact, I think all the bays have an all thread. I think every single bay that I showed has all thread. What I generally do though is I run the all thread on the other side of the plate, just so that it doesn't get in the way of mounting the electronics. So what I generally do is I put the plate slightly off center. So if the all thread is running through, if there's a single piece running through the center, then the plate is offset to one side of it. If there's two pieces of all thread, then they're on the back of the plate as well. So I think all those bays use all thread. It's just the easiest way to arrange things. And it just happened, I just generally arrange it to be on the other side of the plate. The Jolly Logic, it's vastly simpler. Maybe, I don't know. You're sort of limited into what you can do with it, right? I mean, I have not used one myself because I fly mostly high power rockets. But if it works if a rubber band and a plastic parachute works for your rocket, then by all means. I think that as you get to larger rockets and you need larger parachutes, you're going to need a little bit more robust system for retaining them. So I'm not sure how far it scales up, but for whatever it works for, I think it's just fine. I don't have personal experience, so I can't answer too many Jolly Logic questions, but if it works, that's great. So Above 50,000 feet, there's two issues. One is how do you detect apogee, and the other is how do you protect your charges. So there's probably a longer discussion here, but the short answer is black powder is designed to function when there's a reasonable amount of atmospheric oxygen. When you get higher in the atmosphere, there's less oxygen. So if you're going to use a black powder charge at higher altitudes, you either need to make sure the charge is sealed fully so that you carry the ground level oxygen load up with you and it doesn't escape at the lower pressures of the higher altitudes. So what people have done is use surgical tubing and made a sealed charge. You can use black powder that way. You just have to be very careful. What I tend to do when I'm flying higher, though, is I move away from black powder and I go to CO2 systems. So I personally like the system that Tom Rouse used to make, the CD3 system, but there's also one that's sold by Fruity Chutes as well that I just haven't used yet. So you can seal black powder charges to work above 40,000 feet, but generally it's probably about the time where you'd switch over to CO2. No, I don't know. I don't know. There's a question about an ejection charge kit. The 1.4 gram charge is a pretty big charge. That would be a fairly large rocket, so that would open up almost any rocket, maybe even too energetically for mid-power rockets. I don't know I don't know what's in it if it doesn't have hazmat, but if they've made it work, then that's great. But I have not used it. Again, I've been doing this for a long time, so maybe I'm still doing it the old-fashioned way. But yeah, the techniques that I've shown are what I have used. You can't reduce, okay, none of the question about all thread and RF interference. You can't really wrap anything all thread to reduce RF. But what you can do is you can move away from metal all thread. You can use nylon, use multiple nylon threaded rods, or you can use an arrangement where the ends screw into the airframe or the electronics bay and not need a whole piece of all thread. So there's different arrangements. I have not found this to be an actual problem for GPS or telemetry, but in theory, having a piece of metal running parallel to the antenna will attenuate it, particularly when that piece of metal is between the antenna and the receiver. But the thing is, the rocket is a very dynamic system, and as it comes down, it's not going to come down in a single orientation where that rod is going to block your antenna the whole time. It's going to be rotating, and perhaps even rotating in 2 dimensions. So you're going to get signal on the way down, even with a piece of all thread. So I've not found it to be as much of a problem as people make it out to be. Another question, do I like any commercially available bays? I make my own because each rocket is different, and I usually I'm building a rocket that has some unusual shape. I like to build models of sport scale models of sounding rockets. So I tend to have some unique challenge. So usually I'm building my own base. But if there's there's lots of commercial ones out there. So if there's something that looks good to you, I think absolutely give it a try. I don't think there's anything wrong with anything out there. It's just a question of, do you want to build it yourself or buy it? I personally am always on the build it myself because it's what I like to do. Another question about all thread. I have not had this problem. And again, I suspect that while the all thread does attenuate the signal because the rocket is changing its orientation constantly, it's just not a problem. You're going to get a signal from some orientation. Yeah, I saw that. I saw that SMT, that 3D. Lots of people are offering different electronics bays. I think what happens is when you get a 3D printer, you'll be making all your own bays because each one can be perfect. So right now, I make my own bays from either conventional materials or 3D printing, just because it's part of the whole, for me, the construction. But yeah, if you want to buy a ready-made one, I don't see any problem with that. If it works for your rockets arrangement, it's all good. Now, before we get to the end of our time, I want to make sure that I post some links. Now, this kind of talk is sort of more immediate in the sense that we're all together at the same time, but it's harder to demonstrate things. Many things are easier demonstrated in videos. So I've made quite a few videos on the details of these things, and it might be easier to see me actually doing things like wiring charges or testing them or making a bay or how the parachutes are packed and everything. So I've put together some links. So I suggest if you're curious for further reading, you check out some of these links and get more details. I saw a question about black powder. Don't know how to answer it. So I will, then it disappeared. So I will let that one go by. But yeah, so I'll wait for a minute or two for more questions. But thank you for attending the talk, and make sure to check out some of these links because I think they'll make this process much clearer if you can see it in action, as opposed to me just talking about it. Okay, everybody, thanks for attending. Enjoy your NARCON.